What is going on here? Okay, there, that's better. Okay, is that still going? That is still going. Okay. Fortunately, I have to edit this, so I can cut that up. Okay, so... Hello! 3, 2, 1. Hello! I'd like to talk about... Okay, hello. Today I'd like to talk about Theory and Experiment in Gravitational Physics by Clifford M. Will. This is a really good book. This is the book that I would have done as the second book for Physics FM had we gone through and finished quantum paradoxes. So this is an extremely interesting book because what it does is it puts together the theory of gravitation together in such a way that... Okay, well, we can... Still early, we can... Wait a second. Hello! Hello, let's talk about Theory and Experiment in Gravitational Physics by Clifford M. Will. This is a book I really like. This is a book that takes the theory of gravitational physics. Hello, let's talk about Theory and Experiment in Gravitational Physics by Clifford Will. This is a really great book. This is a book that puts the theory of gravitation together in such a way that it can be tested with experiment. Now, obviously, this all happened first through papers and stuff like that, but this is a collection of all of these things. Now, there are two kinds of theory that are going to be looked at here. One are the basic precepts of general relativity, of gravitation. Specifically, the equivalence principles, right? That's the most important part there. So it's going to talk about how you can test the equivalence principle, for example. It's also going to talk about the basic tests of general relativity, the ones that made people think it was true. And then it's going to talk about how to look at astronomical phenomena in order to test different theories of gravity. Now, why would we want a different theory of gravity? Why would we want something other than general relativity? Well, people have always wanted a different theory of gravity, right? Alfred North Whitehead had his own theory of gravity, somebody that illustrious. Milne had a kinematic relativity at one point. There are other ones, Brans-Dicke and stuff like that. These existed for some time. Right now, we have two problems with gravity that may be gravitational, they may be particle physics sort of stuff. That's dark matter and dark energy. We don't really know why they're here, why we have to use these things to model the rotation curves of galaxies, for example, galactic stability, for example, the expansion of the universe, for example. These things need to be modeled somehow, and they can either be modeled by new particles that we don't have any other way to discern what they are, we don't really know what they are, or they can be modeled by problems with general relativity. And so if we find fixes to general relativity, then maybe those can explain what we're missing, right? So there are two ways to do that. And this book talks basically about that second way, that way where we test or we change gravitational theory to try to match the kind of things that we see cosmologically, rather than postulate different material, different matter that we don't know what it is. Very interesting book. This was going to be the second book for Physics FM. So after we got done with quantum paradoxes, this is what I was hoping we were going to talk about. Now, this is the revised edition of 1995. There is a new edition fairly recently that, it took only 20 years or so, maybe 25 to get a new edition out. But, here, what we're looking at is just how this works. So we did, in Physics Frontiers, talk about another thing Clifford Will does, was she maintains a living review of tests of general relativity. And so we talked about that, and I think a lot of that got put into the new edition for this book. So you can check out those podcasts if you want sort of updated information, or actually any information, because I'm just going to go through this quickly, right, and sort of show you what's in the book and let you read it by yourself. But I'm just going to go through and let you see what sort of things are in it. But we talk about the living review of relativity in depth in 1 or 2 episodes. I'm not sure which. We definitely talked about doing the second episode. I don't remember if we did. So let's get to the part you love, which is looking at the table of contents. Everybody loves looking at a table of contents. Okay, so what do we have here for our table of contents? Well, we've got an introduction, and then we go straight into the basic postulates of relativity. The first one is Einstein's equivalence principle. So the equivalence principle, you probably heard it, something like all accelerations are equal to gravitation or something like that. In this case, it's going to be a little bit different, but the first part is just talking about the equivalence principles and its tests. So we come down to 22 over here, right? And it's talking about the equivalence principle. The first thing here is the weak equivalence principle, and that's if an uncharged test body is placed in an initial event in spacetime and given an initial velocity there, then its subsequent trajectory is independent of its internal structure and composition. Okay, so basically all that's saying is that no matter what, something that's falling from this position is always going to fall along the same path, no matter what that thing is, right? So that is another way of talking about that equivalence principle. Then it goes to the weak equivalence principle, or that was the weak equivalence principle. Then they go with the Einstein equivalence principle, which includes a couple of extra terms. There is a strong equivalence principle, and I don't think it's important to get into the difference between that and the Einstein equivalence principle. So the first part of that is the uncharged test body everything falls along the same line. Second is the outcome is independent of velocity of the apparatus. So if you've got a non-gravitational test experiment, then it's going to happen the same no matter what the velocity of the experiment is. It's sort of relativity right there, right? And the outcome of any local non-gravitational test experiment is independent of where and when in the universe it is performed. Gravity is the same everywhere. So gravity is going to act on every object the same. That's the first part. The second part is every experiment is going to act the same no matter how fast it's going. And the third part is no matter where it happens, no matter where you are in the universe, basically everything acts the same. So those are the equivalence principles right there. And that's sort of the basis of relativity. And then he goes through some tests of those principles. And then we get to Schiff's conjecture. That's a very important conjecture. That's an idea. I'm not sure that it's proven to be true. I could have since been proven to be true, but I don't think so. And that's saying that for any sort of coherent idea about gravity that you have, if you have a sort of coherent view of gravity, then that weak equivalence principle will give you that Einstein equivalence principle. And remember, the Einstein equivalence principle is just slightly weaker than the strong equivalence principle, and it's so slightly different. It's very, very little different that I don't think, unless you're an expert already, it's worth going into those differences. Part 3 starts talking about gravitation as a geometric phenomenon. That's the kind of view we have of relativity, right? So general relativity is not just a theory of gravity, it is a theory of space-time. That is, the theory of gravity is a theory of space-time, right? Our gravitational theory is about the geometry of the universe. Okay, it's the way the geometry of the universe is put together. And so that's what Chapter 3 is going to be all about, and that's going to get you to the strong equivalence principle. So you need to know a little bit about that metric stuff before you get there. So now we have a metric theory of gravity, an idea of what a metric theory of gravity is in 3. This is basically the basis of relativity itself and metric theories of gravity. Then we're going to go into this parameterized post-Newtonian formalism. And this formalism is going to give us This formalism is going to give us a way to think about different things. It's going to tell us how we can compare different theories of gravity in a weak curvature region, in a very slight curvature. So we're going to just look at places where the gravity isn't too strong. All right. And we'll go through that a lot. We'll come back to the conservation laws and the PPN formalism. PPN is parameterized post-Newtonian formalism. But that's the way he's going to compare them. So it turns out that every metric theory of gravity, every theory of gravity that can be described by a metric is going to have something like that going on. So that you can look at my notes if you want. All right, then we have post-Newtonian limits of alternate metric theories of gravity. So what that's going to do is it's going to take this PPN formalism and look at different kinds of gravities, right, and to see what they look like. And, one is general relativity, right? One is going to put a scalar tensor theory into PPN formalism. One will take a vector tensor theory and put it into PPN formalism. One will take a bimetric theory of gravity and put it in those formalisms. We did a whole show on one bimetric theory of gravity by Sabina Hassenfelder. And I think our last one actually talked a little bit about scalar tensor theories, or a theory that I thought looked a lot like a scalar tensor theory. Let's see. And then we get to places where we start actually looking at the equations of motions in that PPN formalism. So one, we're looking at the equations of motion for photons. That's going to define our null geodesics in general relativity. Then we're going to look at the equations of motion for massive bodies. That's going to be important. We want to see that the motion is either the same or different in the different theories. If it's different, then we have a way to test the theory, right? Because that's what we care about, is finding some way to test these theories. That's the reason why this is theory and experiment. That's the reason why we have this parameterized post-Newtonian formalism, which is to be able to compare these different theories. Then chapter 7 is the first of the experiment chapters. This one's going to just look at classical tests. The deflection of light, right? That was in 1919. That was the whole reason why people decided general relativity was correct, because it predicted the deflection of light, and people measured the deflection of light around Jupiter. The perihelion shift of Mercury, also a very good one, right? This was something that was already around by that time. So in the late 19th century, people were already trying all sorts of weird things, putting extra planets into the solar system and things like that to try to figure out why the perihelion shift of Mercury was off by a factor of 2. And then there's also a time delay for light. There's a time delay in light, and that actually wasn't looked at. They weren't able to test that until the 1960s. But when they finally were, 50 years later, able to test that, turned out to be just what Einstein predicted. But then we want to go out and we want to look at different things. So then there are tests for that strong equivalence principle, the lunar Atlas experiment, the Nordvelt effect, geophysical tests, orbital tests, and so on. So all sorts of different tests he goes through and looks at that, and you get experimental limits for the PPN parameters, right? And that's going to tell you which of those different theories are viable, or to what extent, or how big those parameters are that we're going to talk about in a few minutes. Other tests of Newtonian gravity, the gyroscope effect, laboratory tests, and so on, post-Newtonian tests of conservation laws, those are in there as well. We care about that. Those are also things that go into gravity. Gravitational radiation is a tool for testing relativistic gravity. This was not available in 1995. And in fact, I don't think it was really available very much when the new edition of this book came out. I'll link to the new edition later on. But it was something that he was talking about directly in the Living Review. He had lots of stuff in there. And, a lot of these things are going on right now. So that's very interesting. If you look at that Living Review, what he's going to say is we can't look at the gravitational radiation in that PPN formalism because the things that are going on that are causing differences in the gravitational radiation and the spectrum for that, those sorts of things are a little bit stronger than the small perturbation that you use for the PPN formalism. So what he does instead is he goes out to further perturbations to look at that. It's just more math to do more perturbations. If you've ever done perturbation theory, though, you know that the math gets really worse very quickly. I'm not sure exactly what order it is, but I wouldn't be surprised if it was an n factorial order, right? So it's the math for additional perturbations gets bad really fast. So you'd probably be glad to not see it in this book. Structure of compact objects like neutron stars and black holes and things like that. Just read a couple of papers all about that. Actually, we're going to talk about something tomorrow where Randy and I, not tomorrow, Thursday, we're going to talk about some ideas about how black holes could have some internal structure and what that means physically. Binary pulsars, another thing that's very important. They get chirping and stuff like that out of that, and other cosmological tests, and just how these were in 1995. Remember, this is in 1995 before they decided they had to have that cosmological constant. So those things might have changed. They probably definitely have changed, and that's another reason to look at that. And then finally, there's the update for the 1995 edition. And, they have all sorts of different things. The Einstein equivalence principle, what's going on with that today in 1995. The PPN framework and other metric theories, tests of post-Newtonian gravity, experimental gravitation. Is there a future, right? And Will actually was building another experiment. I mean, maybe not at the time, but he definitely was part of some other experiments later on. The rise and fall of the fifth force and stellar system test of gravity. The rise and fall of the fifth force. I do not know. I should look at that. So here is another book called The Rise and Fall of the Fifth Force. It was written by somebody else. So, okay, this is revised edition 1993, and this guy is, the original one, I guess, is 1993. So it looks like, to me, the original edition of this and the revised edition of this book came out at about the same time. So I don't know if they were talking to each other or what. Maybe there was a conference paper the year before that said something like that. I'm not sure. Probably actually tells me in this book here. What I did want to talk to you about this in here is about the PPN parameters. So we have this post-Newtonian framework, and it gives you a metric that looks like this. I wonder, do I see... I should not run around looking for it. Let's just say that this is a pseudo-Schwarzschild solution, and if you've ever seen the metric for the Schwarzschild solution, you know it's a lot simpler than this. Okay, it does not include tons and tons of terms. So for Will to actually compare all of these different theories of gravity, he needs a lot of work in there, right? He needs to put a lot of things in there. It's got these alphas and different things. It doesn't really matter if you look at it too much. I mean, you can look at it there if you really, really want to. But I'd suggest you buy the book rather than just stare at your screen if you really want to get into it. I just want you to see that this is large and it has betas and gammas and zetas and all sorts of things. There's a C, there's an alpha, So it has all these parameters. And these things have a meaning, okay? So this is what's really cool, is that when Will put this together, what he's done is he's got this parameter gamma, which is going to measure how much space-time curvature is produced by a unit rest mass, okay? That means basically if I put a piece of mass there, how much of that goes directly into warping spacetime, okay? And for general relativity, that's 1. For these other theories, let's say you have a scalar tensor theory or something, then this guy might go into warping spacetime a little bit, but there's another intervening field, and that other intervening field connects with gravity, and you actually get a little bit less of a warp in spacetime, a little bit less of a curvature because of that. And so that's what that gamma means. All right. This beta means how much nonlinearity there is. That is how much of a deviation from a superposition principle is there. So if you think about gravitational waves, they're nice and linear, for example. So a gravitational wave going this way and a gravitational wave going this way, if they're just pulses, will just pass right through each other. And so in this region where they're passing through each other, there will be some interference, but after they leave, there won't be any long-term effect. However, if you have a nonlinear theory, and general relativity is a nonlinear theory, but with a nonlinear theory, one of the things that can happen, and what usually happens because the theories are not usually very well balanced, is that your interference between these waves will actually deform those waves as they propagate out to infinity, so that you get some interference in the waves as they come to you, and that would be that parameter beta, right? Can you just put two objects here and here, and then say the field here is a linear combination of those two effects? And it turns out for general relativity, where this is 1, it just balances out. Yes, you can just take this and this and say over here, the effect here is the sum of the effects there. But for all of these other theories, for these scalar tensor theories, for these biometric theories, that is not true. Okay, so that's what that beta means. This C is there a preferred location effect? Is gravity different here than it is in the Andromeda galaxy, for example? Maybe even farther away. But that's what that C means. For general relativity, that's 0. That does not happen. Gravity is the same everywhere. For many other theories, gravity is different in different places in the universe. These alphas are their preferred frame effects. That means if something's moving at a different speed in the same place, more or less, will there be a different kind of gravity? And the answer here is no for general relativity, and yes for something called a semi-conservative theory. For conservative theories, these two have to be 0. And the last one is there a violation of conservation of total momentum? None of the theories that he looks at in this book have that kind of violation. So that's the sort of thing he's doing here. Let me see if I can find, I think there's some in the update that are really good. I love these kinds of graphs. It'd be nice to have more of them to show you. These have been updated and they look even more astounding than this does. So you just look at this and you see, okay, this is the time delay. This is the part where we've just said until about 1968 or something, nobody had measured that for general relativity. Then they did. And you see how quickly that starts to converge around 1. And that 1 would give you that gamma equals 1, that a unit mass creates a unit deflection. You see here 2 for the deflection of light, that it also converges very quickly to 1 for gamma equals 1. Actually, it's a complicated thing that is going to be 1 when gamma equals 1. So, again, relativity wins. So relativity wins over and over and over again, which is good. It's a good theory, and everybody loves it. So maybe we don't really need change in it. It's just that, the other things that we've tried to do to explain some of the astronomical data don't work very well either. They don't have really good theories of dark matter. They don't have really good theories of dark energy. So maybe there are ways to change gravity that work out in that way. But this book is going to tell you how much leeway you have, right, in that. How big can those parameters be in that PPN formalism for your gravitational theory? How much can you do with it? And it turns out not very much. You are pretty much stuck with the gravity you have. So, very good book. I liked it. Like I said, was going to be something for Physics FM. We've got lots of podcasts that are related to this book. I'll try to remember to put links for those in the show notes or below the video at some point. I don't know how long it'll take me, but I'll try to remember to do that. I think if you're interested in gravitational physics, this is a very interesting read and something you might want to look into. So that's what I've got for you today. Thank you very much for watching this. I'm sorry it took a little bit to get this out. But there was an issue with the recording. It looks like the recording is going along just fine now. Let's hope it is. The one good thing you get out of that is you get to see the rise and fall of the fifth force, because this was actually at work. So yesterday I went to work and I picked this up and brought it home. So, and now tomorrow I'm going to take it back to work again. So you got to see that book. Maybe I'll show it again later. Who knows? Nice talking to you. See you again some other time. Bye now.